Okay, so good morning, everyone, and thanks, Vladimir, for this very nice introduction, and thanks for saying me that I am an expert and give a contribution. I'm just a user of mesoscopic physics, so I mean, and having trouble with several aspects of this. So, okay, so I decided to accept this, and thanks for the invitation, because for me it's the first time that here in Maryland. And I accepted to do this talk and to show something that, at least in our group, is very recent. So this bunch of experiments have been performed in the last 2 years and a half, okay? So it's something, in some sense, related to old school superconductivity. So, and I hope that you will have some fun looking at these amazing results, okay? So, in this talk, I will discuss about the possibility to achieve field effects, conventional field effects in superconducting metals. Okay, something that has been looking for many years, especially during the 60s and the 70s. Okay, and I will show that there is still a lot of room in order for the understanding and for the let's say the applicational point of view. So let's start with the outline of the talk. So I will introduce superconductivity in the presence of a static external electric field. So basically, what is known, and then I will, after saying that is known very small things, I will go on the demonstration of the first impact, let's say, of electric fields on titanium based devices, and I will show the impact of the electric and magnetic field, okay, on the supercurrent in titanium-based supercurrent field effect transistors. Then I will show that the result is quite ubiquitous in the sense that it can be obtained in aluminum and as well as niobium nitride field effect transistors. And after having shown the results on supercurrent FETs on long wires, I will attack the realm of Josephson coupling. So if showing that it's still possible to have this field effect in short wires dominated by the Josephson coupling. Around the end, I will show that this effect seems to be completely universal in the sense that it does exist as well in proximity metals. Okay, so metals that have acquired superconducting properties thanks to intimate contact with the metallic superconductor, okay? And at the end, I will show the very last result on vanadium-based Josephson field effects, okay, transistors. So this pushes the technology towards very high temperatures of few kelvins. And so in this sense, with vanadium-based technology, as well as niobium nitride, I guess one could really start to think to use this effect toward the realization of superconducting electronics. Okay? I will conclude by giving some suggested schemes for superconducting electronics based on this effect, and then I will give some perspective and conclusions. Okay, so let's start with what is known in superconductivity from old school physics, let's say, physics on the 50s and the 60s in BCS superconductor. So we can say that since the original formulation of superconductivity, around 1935, the London brothers predicted the exponential extinction of an electric field inside the superconductor over the same length as it happened for the magnetic field. So the London penetration depth. Okay. Then they started to do some experiments on this, and they were not able to demonstrate indeed that the electric field is able to produce some sizable or even any modification on the superconducting condensate. Okay. On the other hand, more conventional BCS predictions estimate, in particular by Larkin and Meissner, so 1963. This is why I'm talking about old school physics in some sense. They talk about they estimate the penetration of electrostatic fields in a superconductor, and they estimate the conventional, let's say, lambda Thomas Fermi extinction, okay, the conventional one. On the other hand, I mean, more recent theories by Jakeman and Pike, for instance, Blatter and Feigelman, Lipavsky, and so forth, so on. So let's say the very last are more or less 10 years ago. They discussed the possibility of some influence of electrostatic field in a superconducting condensate, okay, in the sense that electrostatic field remains localized at the surface. I mean, it is, penetrates according to the screening length, but manifests itself non-locally deep inside the superconductor. And this makes sense because, I mean, the superconducting BCS state is something fully correlated. So in some sense, it makes sense that if we touch the skin of superconductor, then it propagates deeply inside, okay? So the propagation is expected to be of the order of xi or a few xi or larger, okay? The important point is that although, I mean, all this bunch of theorists are in principle very interesting, but at the same time are very speculative, no clue so far, let's say, on the possibility to manipulate BCS superconductors or mesoscopic BCS superconductors via static field effect, okay? So now what I'm going to show you that this is not the case. And in principle, if you think to work with a small superconductor, let's say wires or small junctions, so with something that has geometrical dimensions that is comparable to the coherence length or few coherence length, and if the field is sufficiently intense, you can make a big mess inside the superconducting condensate. So this is the message that we want to go. So let's start with our experiments. First of all, so we started a few years ago, this 2 years ago, 2 years and a half, by realizing titanium-based field effect transistors. Okay, these are supercurrent field effect transistors. So this is the general geometry. So you see everything is made of titanium. There is a central channel which is something like 900 nanometers. The width is 200 nanometers. So it's something like more or less 2 coherence length. The width, the thickness is around 30 nanometers. Okay, 35 depending on the sample. Then there is the experiment is performed in a very classical way. So we measure, we drag some supercurrent to the system. We measure the critical current of the wire as a function of Vs, that is the gate voltage applied to the wire. So the system, the first generation, was fabricated on top of a P-type doped silicon wafer in order to apply also backgate to the system. Okay, but then we understood that the backgate is not so important. You just need some very localized electrostatic potential in order to do what I'm going to show. Okay. So just to convince you that the system is very conventional, here is shown the result for the critical temperature, the dark blue line, around 400 milli-K, and the critical magnetic field, upper critical field, perpendicular to the substrate, that is around 120 millitest, okay? So this is a very conventional, let's say, metallic superconductor, BCS superconductor, with a critical temperature that is consistent with the typical parameter of electron beam evaporated titanium, okay? Here is the IV characteristic, so showing of the wire, showing basically the switching current, IC, and the retrapping current at much smaller value. And in particular, in the inset, they show some the full temperature behavior of the critical current in the absence of any field effect. We superimpose the original Bardeen prediction for the supercurrent in nanowires. Okay, so this is just to show that everything is very conventional. So it's not a strange material. It's not a granular material. It's not something that, in principle, we don't know. On the other hand, we understood that we don't know many things about BCS superconductivity. This is the point. So let's. I don't remember. I can tell you what is basically the mean free path, that is around 10 nanometers. And the magnetic field penetration length is of the order of 900 nanometers. But the other length we can calculate, but now I don't remember.
I mean, for most metals, it's really short as well.
Yes.
But like for bismuth or something,
No, I agree.
Low on silicon.
Yeah, because there is they are very poor of electrons. Exactly. Indeed. No, these are very rich of electrons. These are conventional metal, yeah, pure metal. The nice thing is a pure metal. Yes. Yes, exactly. So, yes. So let's try to see what is the behavior as a function of the field, electric field. So here is shown on the top selected IV characteristic, current voltage characteristic that registered at the low temperature, around 5 millikelvin of bath temperatures, okay, is a function of the voltage gate applied simultaneously to all the gates present in the structure, okay, from minus 40 volts up to plus 40 volts. So you see that by increasing the voltage, we obtain a gradual suppression of the supercurrent up the completely full, let's say, quenching of superconductivity in the wire. Here, there is no more trace of superconductivity, okay? What is nice and what is interesting is that this effect is completely bipolar, okay? So there is full bipolarity, and this rules out, in principle, any accumulation or, let's say, enrichment, depletion of charge in the superconductor. It's fully bipolar, okay? There is full bipolarity. This is always what we observe in all the systems that I am going to show you. Then if we study the behavior as a function of temperature of this effect here, that by itself is amazing, you see, I mean, here is shown in this left panel here. So it's the collection of the critical current versus the gate at different temperature, from 5 to 350 milli-K. So you see that indeed is almost bipolar. This shape, of course, there are some imperfection in it's an experiment. It's not indeed a theory. And we see that by increasing the temperature, the plateau increases in general, and then the threshold voltage for which the Johnson couple disappears is almost temperature independent. Okay. And this field effect persists up to very large temperature, 85, 90% of the critical temperature of the superconductor. So it seems something that is extremely hard to kill, okay? Moreover, in order to demonstrate that the field effect exists also in very wide region exceeding the London penetration depth or the coherence length, we made very large platforms of this metal, okay? Something like 4 micron by 4 micron, so 40 coherence length, more or less. And then we apply the backgate, okay? And so you see that in this quadrangular, let's say, shape, rectangular shape, we obtain a suppression of the critical current up to 34, 40% of the critical current, the initial critical current, okay? Of course, here it was applied just with the backgate with a separation of around 300 nanometers between the backplate and the wire. So the intensity of the field, of course, is reduced with respect to the lateral split gates. So this shows the field was applied perpendicular to the field, to the plane of the metal. So this shows that basically the effect is present also in very large region. But of course, the electric field has to propagate in some sense in a direction. I mean, the relevant direction is the thickness, that it is always much smaller than or comparable to the coherence length. Next point, yes.
Regarding the data, why does it stop at that 70 volts?
I beg your pardon, sorry.
Well, the data stopped at 70 volts just because you ran out of fuel?
Yeah, because we are running, I mean, we are putting, I went up to 110 volts in the dilution fridge, and then I stopped because, yes. Okay, so I was, no, but I was a little bit scared to increase too much. On this sample here, the idea was just to show that in principle you can achieve also in very large sample. The relevant scale is the one in the same direction as the electric field, so that is a thickness of coherence length. Okay? So, another interesting point is to test the robustness of the effect in the presence of very intense magnetic field as well, static magnetic fields. So we applied the perpendicular to plane magnetic fields, as you can see here on this graph here. So in the absence of electric field, the supercurrent is weakened up to complete destruction around 120 millitesla. Okay, you see that it's almost symmetric for positive and negative magnetic fields. There are some ripples on top of this. This is no noise. Is called Weber blockade, so is the injection of fluxions in narrow wires that gives up to this. It's the analog of a Coulomb blockade, but for magnetic fluxions in thin wires. Okay, but this is not so interesting for us now. So this is just to show that the critical current just in magnetic field is simply damped and quenched. So if we do the same experiment by putting magnetic fields, okay, each curve is represented by different magnetic fields, and the the gate, the electrostatic gate, the electrostatic field, we see that the effect is very similar to the temperature. So apparently, even though we create some fluxions inside, some normal, let's say, spaghetti made of a normal core surrounded by superconducting supercurrent circulating along it, the effect is still very pronounced. So we can have the same phase. So by increasing the field, the magnetic field, we suppress the supercurrent. But then, I mean, with sufficiently large electrostatic field, we can completely quench the supercurrent. Okay. Here you see that the knee of the threshold for killing the supercurrent is weakly dependent on the magnetic field, and we don't know why. So this is more weakly dependent than with respect to the temperature. Okay. But what is interesting to point out that the effect, the field effect, is persistent up to magnetic fields approaching the critical field of field. So it's a very robust effect. Okay. Another interesting issue is to test the spatial extension of the field effect. Okay. So because one question is, okay, we are saying that mainly is a skin effect, then there is propagation due to the coherence in the condensate. But how much is really propagating inside? Okay. To do this, probably toward this end, one should exploit maybe sophisticated techniques like squid microscopy or scanning probe microscopy in the sense of measure density of states along a wire. Okay, we didn't have this. And we have chosen a different way. So we realize a sort of, you see a comb. And then this is a top view of a comb made of the same material, of titanium, with lateral gates, okay, and back gate as well. So the comb is made asymmetrically. So you see there is a different distance between VS2 and VS1. So we can have many points in distance. We can double the combination of points in distance of the gates. And then the idea was to study the supercurrent in these wires by applying different the voltage. By fixing the voltage, you see how it's damped by moving from this gate to the other gate, okay? So if we define the attenuation parameter, just the critical current without gate minus the critical current without some specific gate that suppresses a lot of supercurrent, we can define, so in terms of percentage, okay? And we plot the point as a function of the distance. For the distance is represented by the average value of the position of the gates with respect to the center of the wire. We can have a curve that shows that, of course, by going far away from the fields, it seems that we are damping quite a lot the effect of supercurrent quenching. And what is interesting is that it seems to have an exponential behavior. Okay, we can fit this with an exponential behavior where the extinction scale is given by the basically something that is a few coherence length. Okay, let's say 700 nanometers more or less. So you see within 2 microns is almost 0. So if you think to some heating effect, of course, this completely rules out any heating, because heating in superconductors, and here there are people working with qubits, many people working with qubits, so they know very well it's a very complicated problem. When you are sufficiently low temperature, the presence of the gap in a superconductor basically weakens drastically the electron-phone interaction in the system. And so whenever you heat one superconductor, this propagates, the thermal length is extremely long in superconductors, tens of microns, okay? Whereas here we have a very clear damping over a very small scale. So it's the first test to say, then if you ask me later, we can discuss the many tests to say that there is no heating, okay? Okay, so it seems that spatially it is damped on a scale that is a few coherence length. Okay, so in some sense, is giving credit to the fact that we need a mesoscopic superconductor to see the effect, not a large superconductor. So this is why maybe the London brothers didn't succeed, because they were using centimeter with something like this cylinder. So. Okay, then if we measure this extinction length as a function of different bath temperatures, so performing the same experiment, different bath temperatures up to below, let's say, the critical temperature, okay, we see that lambda, this extinction coefficient, is constant up to 80% of the critical temperature, and it starts to drop down. Okay, so this basically as I was telling you, this will be a very phenomenological talk. Okay, I will talk the experiments, I will show the experiments, and try to understand and to convince you, and maybe to get together some more deeper understanding of the fact. We tested something very similar on aluminum-based and niobium nitride-based supercurrent field effect transistor. Here on the left, we have aluminum FETs, okay, FETs. So here we are able, just with the backgate on conventional aluminum with a critical temperature 1.5 K, to reduce the critical current of almost 40%, okay, and the temperature up to 400 millikelvin, okay. Whereas for niobium nitride, the 600 millikelvin, still in bridges, made in the same way, and the critical temperature of 10.5 K and thickness of 10 nanometers, we are able to suppress by 40% mostly. So from 90 microamps down to 60, okay. So this phenomenology suggests that the field effect is intrinsic, apparently, to any metallic BCS superconductor, okay. Okay. One quite important question is if it has some relation with the substrate. Okay, so we were and we are becoming crazy in order to understand this effect. So I mean, the role of the substrate can be something important in this case. Okay, so the answer is apparently there is no role of the substrate. So we have tried both doped and undoped silicon oxide substrate with very large resistivity up to 10 to the 4 ohm per centimeter in silicon oxide, and then on pure sapphire, okay, so similar geometry. This is a measurement at 32 milli-K, so the critical current versus the gate for one titanium device made on silicon oxide and on sapphire. So you see, I mean, although the scale is slightly different because it's different, the geometry, I mean, the effect is present in the same way, and as I will show you, the leakage current in the system are completely different. So it seems that it's completely independent of the substrate type, okay? In order to assess this, so we have measured leakage current simply by imposing a voltage at the gate and then measurement the current leak through one of the electrodes with a current amplifier, okay? And what comes out, I mean, that if we compare the same measurement before in terms of critical current suppression, that is a logarithmic scale. So it's the orange scale, and the green one is the power, the leakage power, let's say. We see that on the left again is on silicon oxide, and the right on sapphire. Okay, so we see that basically in the regimes where we have supercurrent suppression, we have that in the case of silicon oxide field effect transistor, the critical current is the leakage current is of the order of 10 to the minus 11 amps. So 10 to the minus 6 times smaller than the critical current for a typical power loss of 10 to the minus 10 watts. But the same effect is present on titanium with a power loss that is something like 4 orders of magnitude smaller. Okay, so this is just saying that, of course, it's almost impossible to prevent any leakage, but this is not at the origin of what we are observing. So next step was, okay, we have shown that in long wires it's possible. Let's try to assess the Johnson coupling. So when the two superconducting leads are coupled through a weak link, really. Okay, so and this is the typical geometry. So these are kind of metallic weak link known as Diem bridges. Okay, because Diem was the first one to realize this kind of weak link, superconducting weak links. And you see, just these were realized on fully insulating silicon substrate, and they are equipped with two lateral split gates made of the same material. Okay, here what we obtained was a pretty nice titanium in the sense it was evaporated. We discovered how to improve the characteristic of these films to improve the critical temperature up to 540 millikelvin and the critical field of 150. Okay, and this thanks to basic vacuum condition of 10 to the minus 11 torr in the deposition chamber and extremely high rates, deposition rates. So, but this is not very interesting in some sense. So again, to convince that the system is, so the typical dimension of the system is the width of the weak link is something like 300 nanometers, so 3 coherence length. the length of the channel is around 1 coherence length, so in some sense it already belongs to the short junction regime, let's say. And the film, these are nice films in a sense. You see the transition is quite sharp for being thin. Then the critical field again is pretty sharp. And here, for instance, you show the behavior of the critical current versus temperature, okay, without any electric field. So you see the conventional damping that is shown here in this curve along with this Bardeen prediction. Okay, so let's see what do we expect for this kind of devices, okay? The Dyen bridge, in some sense, improves the quality of the pancake, let's say. And with the Dyen bridge, we are able to reduce dramatically the voltage required in order to suppress supercurrent, to control superconductivity. So if we look at the general, let's say, phase of the effect, it's very similar for supercurrent wires. So here are shown selected IDs for different voltage bias, okay, from minus 46 to plus 46, more or less. So it shows that is again the full bipolarity of the system, is fully bipolar. And here, in these two bottom panels, on the left and the right, two different devices with slightly different separation of the gate, the split gate from the channel, the superconducting channel. And so we see, I mean, that the general shape is preserved, nice pancakes. By increasing the temperature, going down, so from violet to red, we increase the width of the pancake, okay? Here there is full closing at 32 volts for this second generation device around 7.5 volts, 8 volts. So a voltage that is already comparable to CMOS technology, okay? And again, also in this case here, we see that the gate threshold is independent of the temperature, almost independent. They almost appear at the same voltage and persist up to very large temperatures, okay? This point, again, to go back to the question if it could be some heat in a very vulgar way, ordinary way injected inside, I would say that it seems, the experiment seems to say that it's not a trivial heat injection. And here we show indeed the critical temperature of these wires measured under biasing conditions. So you see the critical temperature is almost constant because if it were just overheating, so some power given to the superconductor producing some breaking of quasi-particles, this would lead a drastic reduction of the critical temperature of the superconductor because it's overheated superconductor, okay? As similarly, if we overcool a superconductor, we can extend the critical temperature of superconductor. So these are very well-known concepts. So if we measure the critical current, the critical temperature is in the same position, independent of the voltage, and if we collect all the data of this, let's say the critical temperature as a function of the gate, we obtain that the spread in the measurement is around 5 milli-K. So what we can say that in principle, within our experimental resolution of 5 milli-K, I would say that is not due to any heating in the system, okay? Or trivial heating, let's say. Okay, so here are some similar results on another bridge. So this is at 50 milli-K, we have the pancake, okay, closing at around 30K. And these are the full IV characteristics in the detail. They show what does it happen when we start to increase the voltage. So the x-axis is the current, okay, and the other is the voltage. So we see that by increasing the voltage, we start to reduce the critical current. When the critical current dies, it starts to appear a resistive tail in the system, okay? So there is, I mean, the measurements are suggesting that there is a sort of intermediate state generated by the presence of intense field, okay? So there is a sort of course, there is a finite resistance, okay? And so our feeling is that the electrostatic fields induce a sort of very homogeneous state inside a superconductor for which some normal region coexist inside the full superconducting part in a sort of NS matrix, let's say. Okay. Again, another interesting thing is the manifestation of bipolarity. This is even more impressive. So these color maps are basically the maps of the critical current versus the two gates, V1 and VG2 of the split gate composing the transistors. And you see that they have almost a perfect square shape, okay? And so these are some cuts along the vertical here on the right and the horizontal on the left. And so you see that there is again, there is, I mean, the different shape. One is rectangular, and the other the square is because depends on how, let's say, symmetric is the distance of, the distance of the two splicates from the channel. Okay, but apart of this, you see that the system seems to possess a completely threshold-like behavior. Okay, so this threshold seems to be completely independent. So whenever the experiment seems to say with actual resolution that whenever you reach some critical field, it doesn't matter the other. So it induces already a sort of a catastrophe inside the superconducting state. Okay, so if we look at in light of possible devices, because people like also devices, and this is good in some sense, one interesting figure of merit is the transconductance of this guy. So how much is the critical current changing with the voltage? So with this first generation, we obtain something like 15 microamp per volt. This is already pretty large. In next devices made of vanadium, we'll show you that probably we can reach 10 times larger or 50 times larger this rate, okay? And this translates in very large variation of the kinetic inductance of the Josephson inductance of the system, because thanks to the electrostatic field, we can control the kinetic inductance by almost 3 orders of magnitude in the same device. Okay, so this in principle is nice, because if we think to use field effect controllable die bridge Josephson junction, we can realize, for instance, let's say qubits, Trasmol-like or Fluxonium-like, where I mean we can control the kinetic inductance with the electrostatic gating. Okay, so this would be a completely alternative technique. So this can be maybe we don't know exactly how noisy will be this qubit. Maybe it's very noisy, but maybe even though it is noisy, it could be useful for other applications inside the superconducting quantum circuit. In any case, no, for instance, to re-equilibrate the states to couple well with the bath, for instance. And so there are several ideas, at least in my head, to try to exploit this for metallic transmos or Josephson traveling wave parametric amplifiers, for instance. Okay, something very similar occurs for the magnetic field behavior, so similar to the wires. So here, the Qs are obtained for different magnetic fields applied perpendicular to the substrate, and of course, on the x-axis, there is always the gate. So we see that the general behavior is very similar also in the Josephson regime. Okay. What is very interesting to understand that seems to support what we were saying before, so the formation of normal region inside the superconducting matrix is contained in these slides, I guess. So here we show the critical current for 2 different devices. It's a function of temperature, and the critical current is measured for different gate voltages. Okay, so the measurement is performed in a different way than before. Okay, so we just fix a voltage and then we shift the temperature. Okay, these are 2 classes of devices. Okay, and you see that by increasing the voltage, going from top to bottom, whereas let's say the behavior of the critical current versus T for no voltage or low voltage resembles, let's say, the Coulomb-Elianchuk behavior for metallic weak links, the more we squeeze, let's say, the superconductor, the more tunnel-like behavior it seems to acquire, like an Ambegawa-Baratov behavior, okay, tunnel-like. So it seems, indeed, that the creation, at least on this kind of geometry, let's say, that the creation of, let's say, normal region insides tends to create, of course, the reduction of superconducting channels driving the supercurrent, so the Josephson coupling. But at the same time, the more normal region we have, enhanced, let's say, the percolative path inside the weak link. And so this apparently is why it behaves a more tunnel-like behavior. Okay. So if we use a generalized relation that allows to interpolate, let's say, between from Aberhorn, okay, from the very clean metallic, so Coulomb-Elianchuk, to the tunnel just by changing the transmissivity D of the weak link, these are the FETs on the right. Okay, so we see that we can reduce the transmissivity, and then we go by reducing the transmissivity. It's just a very phenomenological way to treat the the critical current in the system as a function of the gate voltage, okay, according to this scheme, let's say. So we reduce the transmissivity, and we reduce, of course, the amplitude, but you see the shape becomes, and they can be almost superimposed, okay, one on the other. So this seems to say, and to support the idea that the field has an effect of, in some sense, reducing the transmissivity of the weak link, in some sense, apparently. And then it's very curious that if we renormalize the function of tau of transmissivity for each of the two transistors, renormalize, we plot this function of V gate, where V gate is, each of V gate is normalized at the threshold voltage, we see that they fall on the same curve. So this is something that we do not understand. It is something, of course, very puzzling, but seems, they seem to follow a sort of universal behavior, okay? Good. So now we have concentrated on conventional, let's say, metallic superconductors. Now the idea is to show that the same effect is present also in proximity wires. So in mesoscopic Josephson junction, in particular made of aluminum, copper, aluminum, okay? This is a typical scheme where we have the yellow part that is copper, two very thick banks of aluminum, okay, and just one split gate on front of this, okay? The typical length of these devices is around 800 nanometers, but we have realized stuff up to 1.2 micron with the gate showing the same effect. So here, I mean, is a basic behavior of the critical current as a function of voltage, IV characteristic for different temperatures, okay, from 50 milli-K up to 1K. And there is, you see, the well-known behavior for mesoscopic SNS junction. So there is saturation below certain temperature that is typically of the order of the tau-less energy of the junction. And then by increasing the temperature, there is a strong exponential damping, okay? So the junction more or less starts I mean, the Josephson coupling starts to die around 700, 800 millikelvin. Okay? So it's a conventional behavior for the switching or trapping current of a mesoscopic junction. Now let's see what does it happen in the presence of field. Okay, so a COMSOL simulation of the field in the system with the correct dimensions show that indeed, I mean, we especially did the wire very small in order just to affect the central part of the wire and not the lateral superconducting band. So you see in this common simulation of the fields, the electrostatic fields, that it is mainly affecting the wire, not basically the wire. I mean, or a small portion of the wire, not the bands. Okay. But now here you see are the same pancakes as before. So the critical current at different temperatures versus the gate, and showing this pancake. So increasing the temperature, we widen the plateau, and then at large voltages, it seems that the saturation, there is saturation, so the supercurrent starts to saturate. So what is interesting is that in the SNS structure, so we are never able to suppress completely the Josephson coupling in the system. So we go towards saturation, always. And this independently of the length of the junction. Okay, now I will not show also the length, but this is what we have observed. Okay, and so again, this is ruling out any possible, let's say, trivial heating, because any additional heat also for very large voltage would completely destroy or overheat enormously the quasi-particle population inside the weak link. Here this saturates, and we are talking about 40 volts, 45 volts. Yes? No. Yeah, no. The answer is that we don't have understood this. Well, this is a very relevant question, and my personal perception now, after so many experiments, is that the phase starts to do something very important. So in the system. So probably you are thinking the same direction. And I am quite convinced now that the electrostatic field is acting on the wave function in a non-symmetric way, in the wave function of the Cooper pair. Maybe I will address this at the very end. So creating a sort of phase unlatching. So I don't know if we can talk about conventional phase lift, let's say. Okay, but for sure there is something to my mind related to the phase. Also because we are seeing this now during the last few weeks on experiment performing squids. So we have realized interferometers that we are exactly seeing a strong impact on the phase. Okay, so, but this is just to show you that also in proximity is a complete universal, okay? It's present also in proximity metals, and as well in the presence of magnetic field. So in magnetic field, you see, we decrease the supercurrent, and just this saturation effect is even more present, okay? So there is a very clear saturation. Now we are talking about 80 volts, but if we go up to 100, there is no, basically, variation of the critical current. Yes? Yeah.
Electric field than the real.
Apparently, this is what we are seeing. We can never go to zero. This is the point. Don't ask me why. So, but the demonstration is this. So we have, apparently, even if we exceed 100 volts, it's already pretty large. We can never suppress this, okay? So, and towards this end, we need materials that are interesting. So materials that possess large critical temperature, and to realize, let's say, a sort of superconducting classical electronics, digital electronics, okay? So this is a very recent diamond that we made of niobium with a length of 180 nanometers, width of 120. So the width is something, 3 coherence length for vanadium, that is around 45. Critical temperature 3.65, and the gate channel distance 70 nanometers, okay? So now I want to show you what is the result for this kind of transistors. So we get, they have typically around 1.5 milliamps of critical current at 2 Kelvin. Here we start for 2.8 in our dilution fridge. So we start, you see that we are able to suppress completely the supercurrent below 15 volts. So, and by reducing the distance, I guess we can go down to a few volts, okay? So what is nice, this is already is a voltage range that one can really use in commercial electronics as well as the temperature, because we are a few K, okay? So this sets, to my mind, a new standards in this kind of effect as the operational temperature is really very high, of few K. So based on this, one could think to realize a sort of electric field controlled cryotron, like this, the electron, let's say, for long wires, when the length is much larger than psi, okay? So for very long wires, one can make a sort of electric field controlled cryotron. For short wires, in the Joyson effect, in Joyson coupling regime, one can make a diamond, okay? So the field effect controllable diamond bridge Joyson junction, when the length is comparable to psi 0. So with the first structure, one could implement sort of more conventional digital electronic, classical electronic, whereas with the second one could implement in resonators or whatever to realize a new kind of fully quantum circuits, okay? So if we look at the operation of the electron, this would be simply in this way. So we have a current bias, and then we have a load resistor, where the load resistance is much smaller than the normal state resistance of the device. So when there is no gate 0, okay, the current bias is set that is smaller than the critical current, okay. So when there is no gate, basically there is no signal. This is green, so there is supercurrent flow to the system. When we apply gate, we quench the wire, and there is current out from this lateral part, and we have signal. Okay, so this operates like the original cryotron, but fully field controlled. Okay, so at this point, one can think to construct very simple devices, okay? Like, and with this, construct a full logic based on this system here. So from a copy device to a NOT device, and or, which are two parallel, let's say, electron, and here is one electron and one long wires with different critical current. And then, as, for instance, Hypers is doing now, Hypers Inch in Elmsford, they are doing exactly something similar by using, instead of the electron, the neutron, so with the injection of current. So this kind of electronic can be easily conceived to be in the intermediate circuit between RSFQ and CMOS, or basically without even RSFQ, it's just the full field effect control and then CMOS. Okay? With this, I would thanks for your attention, and thanks again.
I guess this hypothesis would suggest that you have a suppression of the. Okay, you'd imagine that there were some lower line states below delta that are generated by this electric field, which would change the microwave properties presumably, like maybe either dissipation that you mentioned, or maybe at fields before you see suppression, you would see a lowering of the gap. So have you looked at any microwave properties?
No.
Is that a
No, fully static property up to now.
okay? Is that something you?
Lowering of the gap, I would say, would mean lowering of the critical temperature.
Well, but you can imagine that the gap is lower for a few states, and not for most of the states, so that you see it's not changed too much.
You are right. Well, I mean, if it is true that we are creating normal parts, let's say normal puddles inside, of course there is complete suppression, no?
Yeah,
Yes.
no, that's right. But
Yes.
you can go continuously.
Yes, indeed, I would say that would be a very interesting experiment to do a resonator with this guy here, and then to see the dissipation.
Okay.
Right, so to see if we can see the Q factor, how it's changed the Q factor, the frequency, and also the amplitude. This would give a complementary information on this experiment.
They're the same. I didn't distinguish them.
Well, well,
you're just talking about gas temperature.
Yeah.
well, saying this, sorry if I tell you, we are assuming that in principle, I mean, this mechanism that is a static field is inducing some non-equilibrium inside the system.
Yeah, yeah.
That is fancy by itself.
You still have a current going through the device, right? So
No, there is no current going to the device, basically.
well, but like when you check the IC, right, you have some current going through.
What do you mean, the leakage current?
No, just like you measure the
The supercurrent you're saying.
yeah.
Yes, but the supercurrent is an equilibrium property.
It
I would
is
say-
until a point, right? Until the electric fields get large enough. That
Yeah, but we don't know exactly. So I get your point. Indeed, it's my same point. But we don't know. I mean, how is possible? No, immediately. So as I was saying, to my mind, the possibility is that the electric field, basically, I mean, the Cooper pair is delocalized, of course, on the full body, let's say, because the geometrical dimension are of the order of psi. And if the electric field is, or let's say the scalar potential that sees the wave function of the electron whole, they have, I mean, it's a product of the two-wave function in the system. So if the evolution, time evolution, because the potential is not uniform along your superconductor, is different of the two systems, this can create a sort of phase unlatching, I would say. So a different phase evolution, for this, to my mind, is related to something that is due to phase breaking, in some sense, or phase unlatching. So the electric field could operate because, I mean, it's very localized and strongly spatially non-homogeneous, can affect differently the two components of the Cooper pair, in some sense, make a sort of unlatching. If it is true, they unlatch on which scale? They would unlatch on I mean, they are together, the same electron hole, let's say, they are together for a special scale that is of the order of the bi length. This is the point, not of the coherence length. They talk with the coherence length, but they propagate, I mean, they are the same together like at the Debye length, okay? So if they pass, if the material is sufficiently diffusive, like non-diffusive, sorry, with low diffusion like more or less all metallic films, there is sufficient time to go to this sort of, let's say, electric impurity in some sense, no? If you think to this, a sort of electric impurity because it's perturbating the full landscape potential in some sense. And to my mind, I mean, this is something that I have been, I'm trying to realize if it can be really true, this. It can realize sort of phase unlatching in the system. Then so they are completely disconnected at some point because there is too much energy of one with respect to the other. And so the mates are separated at that point. Then they should, I mean, how do you form the condensate? The condensate is formed on a time scale that is the inverse basically of the gap. But the Debye energy, that is the one that is at the origin of all superconductivity, at least as we understood BCS, is much higher, the energy. So the time scale for breaking when they go nearby this impurity is so fast that at the end it propagates all over the wire, and they cannot recombine because the combination time is much slower. And so maybe at some point, don't ask me how, but this introduces a sort of very strong spatial modulation of the order parameter inside, okay? And at the end, when it's very strong, a catastrophe. And then quench. Oh, okay. We are full of questions. Yes.
So your hypothesis is that this is all happening because there's some kind of a new surface state in which the screening is different, the constantly different. And you contrasted that with the BCS prediction, where there would be changes, but really very tiny.
Yes.
But if I understand correctly, that's something that applies to the bulk.
Exactly.
But the BCS theory is going to be consistent with the idea that the electric field is going to penetrate the bulk.
Exactly.
So what does it really mean?
Well, in a thin film, the surface effect is much more dominating with respect to the bulk. Sure. This is the point.
So what you're saying is that this simply doesn't apply. That is, the BCS result,
Yes.
that it's going to be a tiny change. This
Yes.
simply doesn't apply because it's a film.
Yes, it's a film, and what I'm saying that in principle, apparently BCS is not able to describe the effect for thin film superconductivity, the screening effect. So this is for bulk. If you take into account different subbands, probably there are these strong discontinuities at the stairs of the density of states, and this can create a much larger response. But then the point is that your chemical potential has to match one of these subbands in order to give rise to this enhanced reduced screening, let's say. And so in a metal, this is almost impossible. This would be true for a metal poor of electrons, like this fancy two-dimensional superconductor, for instance, where with a real field effect, you can tune the density and then put your chemical potential nearby the band edge. So for a metal, this, to my mind, doesn't work as well. So to explain with BCS, basically what I'm saying, that we would need corrections not of the order of 10 to the minus 8, but of 10 to the minus 2. So 6 order of magnitude larger. So basically, apparently, this is not a mechanism, you could say. Or BCS is not able to reconcile the two different scales. Yeah. No? Mean field and atomic scale.
But somehow BCS is okay for everything else.
Exactly. Yes, but you know that many people failed in 50 years in trying to include electrostatic behavior in superconductivity. If you talk with old school Russian physicists, they will tell you this. I'm serious. And this is true. So, because it's a very complicated problem. Yes.
Then this explanation must predict something for a cold atom system and superfluidity. Does that make sense, or is it really purely condensed matter effect that has something to do with some there are many things that unify titanium, aluminum, and niobium.
Yes, the Debye energy.
Yeah, that's bonus.
exactly. And the Debye energy for all these metals is very similar. It's around 4K, more or less. So this is, I mean, I didn't try yet to make, to realize a sort of, to write down a microscopic theory for this, but I am convinced, more and more convinced that it has nothing to do with the gap of the system, the pairing. So the pairing, you see, is very different. From titanium to vanadium, you have 1 order of magnitude difference. And the fields are almost comparable. And in a proximity metal, there is not even a negative pair interaction inside, no? Yeah, I mean, it's a positive pair interaction in some sense. So there is not really a superconducting pairing, but there is just correlation induced. And there, the voltages of the fields are larger or comparable. So there is not really something directly related to the pairing of the system. And if it is true in the gas that you are saying, that the Debye energy doesn't exist in some sense, no? It's a gas. So, but I don't know, my friend. I'm trying to understand.
I propose to continue discussing over lunch. Okay. Everyone who has an idea how to explain this, please join us.
Yes, I will be very grateful. Thank you. Thank you. Thank you. But we met somewhere, no?
Probably. I mean,
Where?
I've been at conferences, I don't know, several. We have overlapped the site.
But I know your face.
I'm Jay Sao. I do Majorana fermions and that kind of stuff.
I see. I'm Francesco. Nice to meet you.